All right, today we're going to look at coupled systems, which is just an application of Newton's law, and there's really no new theory. We just need to explain how you use this idea to solve a couple of problems. So here's what we have. We have two cars, and I will call one red and one blue. And the masses are given in the problem. Importantly, the red car has a mass of 15 kilograms, so it is the heavier car. And the blue car is a little lighter at 7 kilograms. They're connected by a light rope, and a force is applied to the blue car towards the right. And the force is 44 newtons. And so the question is, what is the acceleration of this system? So we call this a coupled system because it has two objects, a red car and a blue car, and they are connected. And because they are connected, we can assume that they have the same acceleration. So if the blue car's acceleration was different than the red car, then either this rope would be collapsing or breaking, and neither happens. So we assume that this rope stays taut the whole time. So in a coupled system, we assume the accelerations of each component are the same. All right, and it's important to note that we're going to assume that the mass of the rope and the friction forces are negligible. So if the rope itself has no significant mass, it means it doesn't have any significant inertia, which means that whatever force it applies on the blue car is the exact same as the force that it applies on the red car. The forces are equal. We don't need to worry about its mass. All right, so here's how we solve the problem. We start by drawing a free body diagram of both cars. So for the red car, these are the three forces that are involved. We have the mass of the red times g, so notice how it's labeled, m sub r times g. We have the normal force on the red car. You just can't put Fn because there's two normal forces. There's one on the blue car also. And there's a tension pulling on the red car to the right. And because the string is negligibly, the mass is negligible, the exact same tension pulls on the blue car to the left. So here's the blue car. There is a normal force on the blue car, there's a weight on the blue car, and there's a applied force on the blue car to the right. And since both these cars accelerate to the right, we're going to call this direction the x direction. Okay, so this is the y direction for the blue car and the y direction for the red car. All right, so to solve the problem, we're going to apply Newton's laws to each of the two cars. There are two things we do not know. We do not know the tension, and we do not know the acceleration. So simply applying Newton's law to one of these two cars isn't going to give us enough information to solve the problem. So I'm going to apply Newton's second law to the entire system. Okay, so for this entire system, what do we get? Well, the force to the right is F. The force to the left is T. But T also pulls to the right. So when I add up all the net forces, which should equal the mass times the acceleration, the forces are F to the right, T to the left, and T to the right. And you can see these are going to cancel. And that equals the mass of the system, which is the sum of the masses, times A. So what I've done is I've applied Newton's law to my whole system of cars here. Okay? This normal force cancels that weight. This normal force cancels that weight. So in the x direction, we have this. Because these are internal forces, they do not affect the motion of the system. So if these two cars were glued together, we would get the exact same acceleration. So what that means is they cancel, which means we can solve for the acceleration. If those cancel, divide both sides by the mass, and you can plug in your numbers and you can get an acceleration. It's 2 meters per second squared. Now, the important thing to remember is that if the system accelerates at 2 meters per second squared, each car also accelerates at 2 meters per second squared to the right. So we can now apply Newton's second law to perhaps the red car. You could actually do it to the blue car and get the exact same result. But if I apply Newton's law to the red car, the second car here, and I do it in the x direction, the net force in the x direction must equal the mass times the acceleration. Now, we know the acceleration of the red car. It's 2. And we know the mass of the red car, which means if we could find the net force, we could solve it for T. The net force on the red car, however, is just T. So the only force to the right is T. There are no forces to the left. So the net force is T. That equals MRA. Since we know both of these, we can plug those in and we can find the tension. You could have also found the exact same answer by applying Newton's second law to the blue car. You would have had F minus T equals the mass of the blue car times A, and when you solve that for T, you would also get 30 newtons. So here's the conceptual thing to realize. 44 newtons is applied to the system. 30 newtons is the tension in the cord back here. Does it make sense that more than half the tension is back here? Well, yeah. This is a heavier car, and so it takes 30 newtons of force to accelerate it. On this guy, the net force is 44 minus 30, or 14 newtons, so the net force on the blue is 14 newtons, which causes its mass of 7 kilograms to accelerate at 2 meters per second squared. So just a quick note, objects and masses. We think of objects as point entities. The size is either negligible or it doesn't matter to the problem, and we call collections of objects, many objects linked together in some way, we call those systems. So think about how we use the word solar system. Those are objects, planets, asteroids, the sun, which are connected in some way. They interact in some way, in this case gravitationally, but systems are collections of objects. So when you're talking about coupled systems, we're talking about several objects that are connected in some way. Let me solve one more for you. Before I do, a couple of notes. For a coupled system, the acceleration of the system is always the same as the acceleration for each object. And when you consider the entire system, internal forces will cancel. Internal forces cannot cause a system to accelerate. When you consider individual components of a system, objects, then those internal forces between the objects don't cancel, and you can use that to solve the problem. So generally, we want to apply Newton's second law to the entire system, and that allows us to find the acceleration. Once we know the acceleration, we can apply Newton's second law to each object in the system and use that to find the tensions. So let me solve one more problem, similar. I have two blocks. This one is on wheels, which is generally a way to indicate that friction is not significant. But this one, there's no wheels, and so in the AP sort of way of talking, we would say there's a block 1 on a rough surface, and block 2 has wheels. The masses are given, and the coefficient of friction is given here between mass 1 and the ground. We assume the system is motion, and that means we can use kinetic friction, and we want to find the acceleration and the tension in the core between the boxes. So very similarly, we draw a free body diagram. We label it carefully. We need to label it carefully because this friction force is equal to mu times this normal force. The normal force on the blue car does not affect the friction on the red car, so that's why we got to be careful about our labeling. If this car also had friction, we'd probably need to call this FF1 and FF2 to distinguish which friction, but in this case there's no friction on the blue car, so we don't have to worry about it. Notice I've also used M1 and M2, which is common. If you don't want to use letters as subscripts to represent colors, you can use numbers. Sometimes we use capital M and a lowercase m. That gets a little confusing if your handwriting's bad, but it doesn't matter how we label it. I'm just showing you a different way. I'm going to apply Newton's second law to M1 in the y direction. So in the y direction for M1, that's this one here, the normal force minus the weight equals 0, because this is not accelerating in the y direction. I've chosen the x direction as the direction of acceleration, so by definition the acceleration in the y direction is 0. That just means that the normal force on car 1 is m1g. Now, let's apply Newton's law to the system in the x direction. Forces to the right minus forces to the left equals equal ma. So forces to the right are F. Minus T is to the left. This T is to the right, so it's plus F. And then the friction force is to the left, so it's minus the FF. That is the net force. That's got to equal the mass of the system times its acceleration. Notice that the T's, the tensions, cancel. They're an internal force. Friction is not an internal force. It doesn't cancel. For friction, we're going to use mu times the normal force, which is mu m1g, because up here we're able to show that the normal force on block 1 is m1g. I'm going to substitute that in for the friction force. So when I rewrite it, canceling the t's and substituting in the friction force, I get this expression. I can solve that for A. I can plug in my numbers and get an answer. So it's 1.27 meters per second squared. Now I know the acceleration of the system. That is the acceleration of each object in the system if they're a coupled system and the cord does not break. So I can now apply Newton's law to either mass. It doesn't matter which one. I chose to do it to a mass 2. So if I apply it to mass 2, I can find T. So forces to the right are F, forces to the left are T. So F minus T equals the mass 2 times A. I know M2, I know A, I know F. I can find the tension T. Just rearrange, plug in your numbers, and you get 16.2 newtons. So what you're going to do, and this is the first of 2 assignments involving coupled systems, is you're going to solve problems with coupled systems where the objects are accelerating in the same direction. So you'll have some practice doing this. Make big, clear, neat free body diagrams to illustrate exactly what's going on. Do not draw the free body diagram on top of the graph, the schematic you're given. Draw a separate free body diagram, carefully label it, and then apply Newton's law, making it clear what you're applying Newton's law to. Am I applying Newton's law here to M1 or M2? Am I applying it in the X or the Y direction? So make that clear to the grader and then do it. Sometimes you're not exactly sure what you're doing. Maybe you would have started with this thing here and you would have gotten stuck because you don't know FF. So then you would have done it in the X direction here, or the Y direction here, to find out the normal force is M1G, and you could plug that in here and continue. All right, so that's going to be your job, is to solve problems with those kinds of ideas.